Welcome guys, today we are going to do some practice with periodic trends, but before we jump into actually comparing the properties of elements to each other, let's review a little bit of what's going on with the periodic table and the trends. So rather than jump right into the properties themselves, let's talk about some of the things that are going on with atomic structure that's the underpinnings of why these properties display periodic trends. So the first thing I want to look at is ENC. Now ENC is my abbreviation for effective nuclear charge, which is a scientific way of saying the force of attraction between the nucleus and any electron in question. So as you consider what happens going across a period in the periodic table, every time you move over one, you're adding a proton. And yes, you are adding an electron, but the attractive force provided by the protons is the main thing that counteracts here. So, as we go across, effective nuclear charge increases. Okay, and then distance from nucleus to outermost electron, and I really should have said electron cloud or orbital. Okay, you have to remember that on a particular row, each row represents an energy level of electrons. So hydrogen and helium only have one energy level of electrons. When you get to row 2, they have 2 levels. Row 3 has 3 levels. But, like if you're just looking at row 2, 2 s electrons and 2 p electrons, their clouds are approximately the same distance from the nucleus. So we're not significantly changing the distance as what happens when you go down the group. So for here, I'm going to put stays the same. Alright, also there's shielding, and if you'll recall, shielding is is another way of saying repulsion between electrons, because they're like charges and they don't want to be anywhere near each other if possible. Okay, so as you go across the period, shielding is not an issue. I mean, there's a tiny bit of change, but it's not enough to make an impact that we have to worry about. So we're going to list that as stays the same. So now that we've got an understanding of what's going on with the structure of the atom, now it will make more sense to what the periodic trends actually do as you go across. So atomic radius is going to decrease as you go across. Now the reason why that happens is because, as we said, the effective nuclear charge, aka the force of attraction, increases as you go across. And so what that results in is that the nucleus is more able to attract the electrons, drawing them in closer. So as you travel from the left side to the right side of the periodic table, the sizes of the atomic radii are going to get smaller and smaller and smaller. Ionic radius follows the same trend, but there's a little bit of a caveat you have to remember with this. And so let me add a little bit to our periodic table here. So on this side of the periodic table are the elements that form cations. Over here in this little section are the elements that form anions. And then I'm going to kind of cross out our noble gases here because they don't form ions at all. So you won't have to worry about those appearing in a question. So what happens is that the size of your cations starts large, and then by the time you end up over here, it's smaller. But then, right here you hit the elements that form anions, and so the radius is large again, and in fact it's significantly larger than the cation over here, and then these are going to decrease as you go across. So big thing to remember, that anions are significantly larger than cations. So don't get that confused when we're talking about atomic radius versus ionic radius. If you've got a charge on it, then you have to remember this. If it's a neutral atom, then you can just go by the fact that it decreases going all the way across. Alright, the next property is electronegativity, and that is how well an atom is able to attract the electrons that are part of a bond. And so this goes back to how well it can attract its own electrons, because the more effectively it can attract its own electrons, it will be more effective at attracting those in a bond. And so this also ties to the fact that effective nuclear charge is going to increase as you go across. So as that increases, that's another way of saying the force of attraction increases, those things have a tighter hold on their own electrons, and so they're also more effective at attracting those in a bond. So electronegativity increases as you go across. Ionization energy is the energy required to remove an electron from the outermost energy level. And so this also ties to how well does it attract its own electrons. The more tightly that nucleus is able to attract the electrons and pull them in, the harder it's going to be to remove one. And so it's going to take increasing amounts of energy to do that as you go across. And so ionization energy also increases. Alright, now let's look at what's going on going down the group. Alright, so let's, like we did with the other one, address effective nuclear charge. Okay, as you're going down, you are adding significant numbers of protons, but you're also adding electrons, and those electrons are being added at increasing distances. Because you have to remember, when you go down the group, the electrons here in 3p are farther away from the nucleus than the ones that are in 2s. And so every time you drop down, you're increasing that distance, and so what you end up with is actually a decrease in effective nuclear charge. And then I'm going to put my little note that distance from the nucleus to outermost electron, we're talking about the cloud or the orbital, not the electron itself. That is going to increase as you go down, because like I just said, you're adding energy levels of electrons in clouds that are located farther and farther away. And then also, as you're adding significant numbers of electrons and you're adding energy levels in between the nucleus and the outermost electrons, your shielding becomes a factor and it increases as you go down. So then, atomic radius, okay, as you go down, you're adding energy levels, so the electrons are located farther and farther away, and so atomic radius will increase. And ionic radius follows the same pattern. It also increases as you go down. Electronegativity, since our force of attraction is decreasing as you go down, the ability to attract its own electrons is going down, so it's not going to be very effective at attracting those in a bond either. So electronegativity decreases. Then ionization energy, if that's how much energy it takes to remove an electron, so as it goes down, if it's losing force of attraction, then it's going to become easier and easier to remove an electron. So your ionization energy is also decreasing as you go down the group. So now that you have these, you can use your knowledge of this and apply it to these sets of atoms. And in the first question, we're going to rank them from smallest radius to largest radius. Now you may have noticed that your screen just changed a little bit. I paused my recording and I filled in on our little periodic table here the elements that we're actually going to be looking at so as to help us when we're answering these questions. So the first one, we're comparing lithium, carbon, and fluorine. So these elements are located on the second period, so lithium, carbon, and fluorine. So our trend in atomic radius is that it decreases as we go across. So that means the farther to the right, the smaller it's going to be. So of these three, fluorine will be smallest, and then we work our way backwards to get the increasing size. So then carbon would be next, and then lithium would be the largest of those three because it's all the way on the left-hand side. Alright, for set B, we are looking at three elements that are in the same group, lithium, sodium, and potassium. Now the trend for atomic radius going down is that it increases as we go down. So since lithium is higher in the group, it will be the smallest. And these are actually written in correct order as given. Alright, in question C, we are comparing germanium, phosphorus, and oxygen. Now, this question may be a little confusing at first because you're not comparing elements that are in the same row or in the same column. However, we can use our logic to figure out which one is which. So, germanium has 4 energy levels of electrons. And those 4p electrons are going to be located much farther out than the electrons for phosphorus or for oxygen. So we can go ahead and decide that's our largest one, so I'm going to write that one out here to the end. So then we're comparing phosphorus and oxygen. Well, oxygen is in a higher row and is one column over. So we know that oxygen is going to be smaller than phosphorus. So phosphorus is our middle one, oxygen is the smallest. Alright, for these next three, you can pause the video in between the answers so that you can try to work these out yourself. So for D, you're comparing the atomic radii of carbon, nitrogen, and aluminum. So carbon, nitrogen, and aluminum. So pause your video and see if you can get the answer. Okay, so aluminum is the element that is located farthest to the left and the lowest down. So we know aluminum is going to be the largest of the three. Oops. So that means we just have to compare carbon and nitrogen. And since nitrogen is farther to the right, nitrogen is going to be smaller than carbon, so nitrogen should be listed first, carbon second. Alright, for question E, we're looking at aluminum, chlorine, and sodium. Nope, it's not sodium, excuse me. Aluminum, chlorine, and gallium, my bad. So pause the video now and see if you can put these in the correct order from smallest to largest radius. Okay, in our process of elimination, we know that the farther to the right it is, the smaller it is. And since chlorine is farthest to the right and it's higher up than gallium, we know that chlorine is going to be the smallest of our three. Then we can go back and compare aluminum and gallium. Since aluminum is above gallium in the periodic table, directly above it, we know that aluminum is smaller than gallium. So aluminum will be our second, and then gallium will be our largest. Alright, for question F, you were looking at beryllium, francium, and fluorine. Pause the video now and see if you can put them in the correct order. Hopefully you got the right answer. So our smallest one is going to be the one that is farthest to the upper right hand corner, which is going to be fluorine. Then we have to compare beryllium and francium. So since francium is so much farther down on the periodic table than beryllium, we can be sure that beryllium is smaller than francium. So beryllium second, francium last. Okay, for the remaining questions, since I don't have the periodic table up on my screen, it would probably be a good idea for you to have one to look at. So our next question, we are ranking sets of ions from smallest radius to largest. And of course I managed to put the first one as being somewhat of a tricky question. We've got magnesium ion, silicide ion, and sulfide ion. Well, those three elements are all in the same row. And remember what I said earlier about the cations being significantly smaller than the anions? Well, we can go ahead and put magnesium first. And then we're down to comparing the two anions. Since sulfide, coming from sulfur, is located farther to the right-hand side of the periodic table, we know that one is smaller than the silicide. So these are actually written in correct order as given. Now, looking at the magnesium, calcium, and barium ions, these all come from elements that are in the same group. They're in group 2. And so remember that atomic, like ionic radii, increase as you go down. So the element that would be highest in the group is the one that's going to have the smallest radius. So magnesium would be first, followed by calcium, and then barium. In C, we're again looking at elements that are in the same group, so I would pause the video now and see if you can put them in the correct order. Alright, looking at group 17, fluorine is the very top element, so that must mean the fluoride ion is going to be the smallest. And as you go down, chlorine is the next element, so chloride ion would be second, and then the bromide ion would be the largest of these three. In D, I actually made a typo and put the same ion twice. So we're really only comparing barium ion and copper 2 ion. Now you may be wondering why I just said barium and here I said copper 2. Well, copper is a transition metal, and the majority of transition metals are capable of forming multiple cations. Barium, on the other hand, is a group 2 metal, and group 2 metals always form a positive 2 cation. So copper actually usually forms either copper 1 or copper 2, so we have to be specific. So if we look at those on the periodic table, copper is in the 4th row, farther to the right than barium, which is almost all the way on the left in the 6th row. Because barium is much lower down and much farther to the left, we are pretty certain that the barium ion is larger. So copper 2 ion would be the smaller of the two. Alright, for E, this one's a little tricky. We've got copper 1, copper 2, and nickel. So in this case, it may be easier for us to figure out which is the largest ion first. And if we look at the periodic table, nickel is located to the left of copper. So that means the nickel 2 ion is going to be larger than either of the copper ions. So I'm going to list it there on the end. So then that comes down to, well, which one of these two is going to be smaller? So what you have to remember is that when cations form, neutral atoms lose one or more electrons, the more electrons that they lose, the greater the boost is to the effective nuclear charge. Therefore, the force of attraction increases. So since copper 2 lost more electrons, it experiences a greater boost in its force of attraction and is able to draw its remaining electrons in closer. So copper 2 will be the smaller one, and then that leaves copper 1 as the one in the middle. Right, for F, you guys should be able to do this one on your own since these elements are all in the same row. I would pause the video now and see if you can do this one on your own. Okay, on period 4, we've got iron, cobalt, and zinc. And since zinc is the one farthest to the right-hand side, the zinc ion is going to be the smallest. And then working our way backwards, cobalt, and then the largest being the iron 2. In question 3, we're considering ionization energy. So recall that the greater the attraction is between the nucleus and the outer electrons, the higher the ionization energy is going to be. So in A, we are looking at magnesium, silicon, and sulfur, all elements that are in the same period. And then the trend for ionization energy is that it increases as you go across, which corresponds to that increase in effective nuclear charge. So sulfur is the one that is farthest to the right. So that one's actually got the highest energy. Magnesium is the one that's farthest to the left. So magnesium is smallest, silicon in the middle, sulfur with the largest. For question B, we're looking at the elements that are all in group 2. And ionization energy decreases as you go down the group because that increase in size is also coupled with a decrease in attractive force. So barium is going to have the lowest. And then working our way back up, magnesium will have the highest. All right, for question C, we are looking at elements in the same group, so I would pause the video here and see if you can put these in the correct order. As we just did in B, the element that is closest to the bottom of the group is going to have the lowest ionization energy. So our lowest one here is iodine, and then working our way up, chlorine, and then fluorine having the smallest of the 3. In question D, we're looking at barium, copper, and neon. Now, these things are not in the same group or in the same period, but they are spread out enough in the periodic table that you should be able to figure this out. So pause the video, see if you can put them in the correct order. All right. Since neon is the element that is closest to the upper right-hand corner of the periodic table, we know that it is going to have the highest ionization energy. Barium is in the opposite corner, so barium is going to have the lowest. And since copper is somewhere in the middle, it's our second element. In E, we are looking at silicon, phosphorus, and helium. Pause the video and see if you can put these in the correct order. Okay, so we established that the closer you are to the lower left-hand corner, the lower your ionization is going to be. So looking at our choices, silicon is the one that is farthest to the left, so it's going to be lowest. Phosphorus will be in the middle, and helium is going to be our highest ionization energy because it is located most towards that upper right-hand corner. All right, in F, we are looking at germanium, antimony, and arsenic. So pause the video and see if you can order these. Okay, when looking at these, antimony is located below arsenic, and then germanium is to the left of arsenic. Okay, thing to keep in mind is that the difference in values as you go down a group, there's a more significant change from one row to the next row than there is when you go across a period and you go from one group to the next group. So antimony is actually going to have the lowest ionization energy, and then followed by germanium, and then arsenic having the highest of the 3. All right, next we're going to look at electronegativity in number 4. And the thing you need to remember is that noble gases do not have an electronegativity value. It is true that xenon and krypton have been forced to form compounds with fluorine in lab settings, and so we do have an electronegativity value for those, but the rest of them do not. So for our purposes and prediction purposes, I want you to assume that any noble gas that I give you has no electronegativity. So let's look at set A. We've got lithium, nitrogen, and carbon. And so electronegativity is the measure of how well the atom attracts the electrons that are involved in a bond that it's bonded to some other atom. Well, the more effectively it can attract its own electrons, the more effectively it's going to attract those in a bond. So that goes with our effective nuclear charge increasing as we go across. So electronegativity increases as we go across. So out of these three, the element located farthest to the right is nitrogen. So that's going to be our highest value. Farthest to the left is going to be our lowest value. So our lowest is lithium, followed by carbon, and then nitrogen. Alright, in B, we're comparing carbon, oxygen, and neon. And so we need to remember what we said about noble gases. So Ne has an electronegativity of 0, so it's going to be the lowest. And then comparing carbon and oxygen, since carbon is farther to the left-hand side, carbon is going to have a lower electronegativity than oxygen. And oxygen is one of the most electronegative elements. That upper right-hand corner of elements excluding noble gases are the elements with the highest values. Alright, so question C, we're comparing phosphorus, oxygen, and silicon. So pause the video and see if you can put these in the correct order. Alright, phosphorus and silicon are both located on period 3. And of those two, phosphorus is the one that, silicon is the one that is located farther to the left. So silicon is going to have the lowest electronegativity, and then phosphorus, and then oxygen will have the highest of the three because it is farther to the right and higher up. Alright, in D, we're looking at potassium, magnesium, and phosphorus. Pause the video now and see if you can put them in the correct order. Okay, our element that is farthest to the left and lowest down is potassium. So potassium is going to have the lowest value, followed by magnesium, and then our highest value is going to be our phosphorus, as it is the element that is farthest to the right. In E, we're comparing sulfur, fluorine, and helium. So pause the video and see if you can put these in the correct order. Again, we have a noble gas, so helium is going to have our lowest value of 0. So then we have to compare sulfur and fluorine. Since sulfur is farther to the left and lower down, sulfur is going to be lower than fluorine. And in fact, you need to remember that fluorine is the most electronegative element. It has the highest electronegativity value. In question F, we're looking at germanium, phosphorus, and arsenic. So pause the video and put those in order. Alright, our element that's located down the lowest and most to the left is germanium. So it's going to have the lowest value. Then arsenic, and since phosphorus is on top of arsenic, phosphorus will have the highest value of these three. Now, in our last set of questions, we are talking about effective nuclear charge, and so I've been referring to that as we go along. And recall that effective nuclear charge increases as you go across, and then it decreases as you go down. So question A, we're looking at xenon, strontium, and tin, and these are all elements that are located in period 5. So pause the video and put them in order. Okay, the element that is farthest to the left is going to have the lowest effective nuclear charge, so that's going to be strontium, and then tin, and then our highest effective nuclear charge on that row is xenon. In B, we are comparing bismuth, oxygen, and nitrogen. So pause the video and see if you can order them correctly. Bismuth is located lowest in the periodic table. It is several rows lower than oxygen or nitrogen. So bismuth is going to have the least effective nuclear charge. And then since nitrogen is to the left of oxygen, nitrogen will be second and oxygen having the greatest. In question C, we're comparing noble gases. So pause the video and put those in the correct order. So our least effective nuclear charge is going to be our noble gas that's located lowest in the column, and that would be radon out of this set. And then as we work our way back up, we get to krypton, and then of the three, argon will have the highest effective nuclear charge. And then finally, set D, we've got chlorine, aluminum, and sodium, which are all in the same row. So pause the video and put those in order. Sodium is located farthest to the left, so we know sodium has the least effective nuclear charge. And then as we travel across, we get to aluminum, and then finally chlorine having the greatest of this set. Hopefully this practice will help you as you answer your homework questions, and feel free to email me if you have any questions, and I will see you in class.